Hello everyone, so welcome back. This is DS612. So today I'm doing a video record for this logistic model for you guys because we are basically having a Thursday off. So I just want to make sure that we cover some of the chapter 4 topics in this video so you guys are not falling behind too much. But generally speaking, we are just trying to use this probably about 30 minutes of videos or maybe 40 minutes to cover this concept of logistic modeling. So we would like to actually first think about chapter 4. We are trying to resolve a problem, and this problem is usually what we call a classification problem. So the classification problem actually is the types of problem you are going to encounter a lot, especially in the industry. There are a lot of things that you want to categorize, you want to actually classify into a different ranking, different range, different classes. So you will use these statistical methods to actually tell your employers how to classify certain things and what defines as a unknown data point in your maybe in your pool of data. Let's say a customer joins in a company and you want to classify whether this customer should usually buy a very expensive luxury goods in your website or maybe a very cheap low-end product. So we will begin with a very simple questions here. So the first question we would like to ask is, if we are going to have a classification problems, the response variable that we have, it's no longer in terms of quantity. So remember, in chapter 3, we have covered the linear regression model, which is superior when we are dealing with quantitative response of y. But now, if we are telling you that the y, the response variable in the model, it's no longer any real numbers that we actually define in the world, but indeed, it only have maybe 2 values in the simple case. So what if we have a y response variable that only have 2 classes in this case, which is 1 and 0. When the y actually takes a value of 1, we actually say that, well, this example we use in the books, we are using a default credit data sets in the books. We say, well, this person will have a classifications, right? So it's defined to be a person who defaults before. And this data will have the individual value of y for that person. When it takes a 0, that means, well, this person has never filed a default for his or her payments. So in this data set, obviously, well, this 1 and 0 cannot be interpreted as a quantitative values. It's not like 1 is representing some number and 0 is representing another number. 1 and 0 basically just define whether it belongs to class 1 or class 0. Well, can we actually do a linear regressions for this kind of response? The question is actually easily answered, because this is data. As long as you have a variable that actually vary, whatever the response variable is, as long as it takes different values, we can still use the linear regression model. But I would like to point out that there might be one very important question we have to consider when we're using a linear regression model for this type of problem. Well, let's take a look at the regression model's approach here. If we are going to use a linear regression model, our response will have 2 values, right? Either 0 or 1. But in this case, we are not trying to plot a line that actually fits all the data point here. Instead, well, we are trying to basically use a line to plot the probability of y, how likely the probability that y will become 1 and y will become 0. So that's the concept of building this classification model in a linear regression backgrounds. So we are basically talking about conditional probability here. Let's say we have some feature x that we pass into our model to predict y. And this probability that we are trying to predict here is the probability of y is equal to 1 when given x is given some value. Let's say, for instance, we actually have a graph right here that kind of demonstrates, well, the data point, how it's scattered around on the graph between x and y. Well, we see y can only take the value of either 1 or 0. Right? It doesn't have any other value between it or beyond it. So in this case, what we are trying to do in the linear regressions models, we are trying to plot a regression line that can most likely fit in all the data points in a straight line. And as you can imagine, so the line might look something similar to this one. Or maybe something that you actually go beyond a little bit, right? A little bit steeper slope that we can actually cross more data points. Right? So something like this, like a straight line. So we can actually have the probability of y modeled by these lines here that has an intercept of beta 0 plus beta 1 times x. So it's a linear line. And obviously, this linear model suggests we are trying to minimize the distance of every single data point to our regression lines. So the distance, the mean square error is being minimized, right? So the error term is being minimized in this model. But as you can tell, this is definitely not the perfect models. Well, there are two problems, generally speaking. So issue with the linear regression models. Number one, obviously, the fit of the model is not the best. So the fit of the model basically tells you how well this line fitting data point, and obviously it's not fitting pretty well. They're pretty far away, right? Most of them. So nothing actually lands on the line in this case. Another issue for this linear regression model approach is that this model suggests the probability of y is equal to 1 when given certain x value. There is a possibility for this probability to go beyond 1. And at the same time, this probability when y is equal to 1 given some x value can possibly less than 0. And when do you see that? So for instance, we take some x value here, some x1. We look at the regression lines, and obviously this prediction here tells us y can be above 1. So that means the probability for this y to happen, it's beyond 100%. It's over 100% of the probability that it will happen. And when do you see a point where the prediction tells you the probability will go below 0? Well, let's take a look at some x2 right here. So this x2 value actually given the fact that the y value can actually go below 0. So the probability y is equal to 1 when x is given as x2, it's way below 0%. So 0% is the lowest chance when we talk about probability. So nothing can go below 0. So in this case, because of these two issues, it's very difficult for us to accept the fact that the linear regression model approach is a good one to this kind of response variable. Or in this case, we call this a classification model. So how are we going to resolve these problems? Well, in the textbook, we are going to take the first approach to kind of think about, if we cannot come up with a straight line that can model all these data points very well, maybe we should consider a functions that can actually maybe getting very close to 0 at some points and getting very, very close to 1 on the other points. So that means whatever x that we pass into this model, the range of y values, the predictions of y values should always be within the range of 0 and 1. So how? Well, fortunately, we do not have to come up with that math to understand there are several functions that work that way. Well, indeed, today we are going to talk about the one that is most likely going to be used. And this model is what we call the logistic model. So in order to understand how the logistic model works, we can actually use this logistic functions. So we have a functions here. So the functions basically suggest we can actually evaluate the probability of y is equal to 1 when some x is given, when actually we have a logistic functions that give us the value of range of y that's always falling between 0 and 1. So this functions here, it's basically what we call a logistic functions. And as you can see, the form of this function looks a little bit complicated, but it has some very, very interesting element here. As you can see, the functions tell us the probability can be used to calculate when we have the base of e to the power of beta 0 plus beta 1 times x1 divided by 1 plus the e base to the power of beta 0 plus beta 1 times x1. So in this case, we actually have a function that looks really, really similar to the linear model, at least on the power base. And then we try to do some eliminations, right, manipulations of these equations. We play around with the algebra, and we can actually come up with an equation similar to this. So it's a transformation from this original logistic function to these functions here. Well, here we have the probability functions divided by 1 minus the probability, exactly the same thing. So in this case, you can actually think about this as the odds for y is equal to 1. How? Well, you can actually rewrite these functions like the following. We can say this is basically the success rate divided by 1 minus the success rate. So if you have a probability, let's say 30% of a chance that you will actually have a person file a default, right, when y is equal to 1, and divided by 1 minus the 30%, the leftover, which is 70%, which means the probability this person is not going to success, or in this case, it's categorized as not going to file a default. The rate of success divided by the rate of failure, this is basically what we call the odds. So the odds basically tell us about the probability, how likely something is going to happen. And in this case, this odds, because by algebra we are transforming to equation 2 here, we actually get this very nice and clean equations. It's basically just the base of e to the power of beta 0 plus beta 1 times x1. Well, at this point, hopefully, I do not have to explain too much to you guys because I'm going to do one more transformation to make this a linear format. So the next equation I would like to use is basically take out the base of e from this side. In order to do that, you basically take the log. And given the probability of y is equal to 1 given some x, divided by 1 minus the probability of y equals to 1 given some x, equals to, well, since you take the log on one side, you take the log of the other side, so the log to some e base is going to cancel out. So all you have left is basically just beta 0 plus beta 1 times x1. And now we are getting to the final stage of this transformations. This part right here, it's what we call the log odds. And sometimes we actually call this a logistic function because this is the log of the probability that our model can predict whether the y is equal to 1 or not. So that's why we actually give it a name. We call this a logistic model. Well, at this point, well, we are basically trying to understand where we get the estimation come from, right? What's the idea behind. As long as we can define this logistic function here that can always limit the range of y value from 0 to 1, right? Whatever x that we pass in, we always take a value of either 0 or 1. Then this will be a way how we can resolve the problems. We can actually model this log odds in a linear format. So graphically, I would like to suggest you guys to think about this logistic function. So this function here is going to take equations looking similar to this one. So the equations there will look something similar to this. So this logistics functions is never going to touch the 0 on the x-axis. And also, this end of the y will not touch when y is equal to 1. So that means you will always get some value between 0 and 1. So in this case, we can actually use the functions to fit the data. But not only just that, this functions is called logistic functions. And in statistics, this is one of the functions we define as a probability density functions. So this probability density function actually allows us to have the interpretations of the graph. So for instance, we are giving some x right here, some xn. We want to note what's the odds, the probability y is equal to 1. When we look at these functions, we are basically referring to the density of these functions from all the way to the very negative infinity to this point, xn. And we are trying to capture the probability that happens on this tail. And this probability here basically tells you the probability where y is equal to 1 when given that x is equal to xn. So for instance, if our estimation is about 0.333, that means 33.33% of a chance that y will be equals to 1 when we have a feature value of x equals to this one right here. So the interpretations is actually quite important to note in the logistic model. Right now, what we are trying to explain here is basically giving you a complete framework of how we are going to model probability and how we use probability to define the classification problems. And I would like to use some example to try making you do the math so that you understand how we get this number of 0.3333 when you actually seeing our result outputs. So let's see if you can solve the following problems. All right, so we are coming here to actually take a look at some of the examples from the textbook, so you can actually try to read through the contents of the textbook and while you are following the videos here. So the first question we ask is, let's say we try to put some predictors in our model, and we're trying to predict the default probability. And using the textbook example, let's say we have a predictor here, balance. So balance basically refers to the balance of the in that person's account. So how much of a balance this person has by the end of the month, maybe on an average. And we want to know if there is a person that has $1,000 of money in his bank account. How likely this person is going to file a default if given the fact that default is only going to be predicted by balance, this predictor here. Well, the way how we want to interpret this betas or estimate parameters, it's very, very different than the linear regression model. The reason is because we are not trying to fit a line to all the data points in this model. We are trying to use the features, the predictors, to predict or to estimate the probabilities of why is going to happen, or the response variable going to happen. So in order to understand this problem here, you have to actually remind yourself, when I'm trying to calculate the probability here, where y is equal to 1 given that x, in this case, is given the balance, which is $1,000. The logistic function actually tells us, we don't actually just say, hey, let's add up this number together. The logistic function actually suggests we have to get the probability by using the original logistic functions. The simpler form that we make a transformations earlier, it's only for you to see how we can actually make it a linear model. But now, when we're talking about this estimate in a linear form, we have to put it back into the logistic functions. So in this case, we have to use e to the power of negative 10.6513 plus 0.0055 times 1,000 and divided by 1 plus e to the negative 10.6513 plus 0.0055 times $1,000. So that's how we are going to use our estimated parameters, the betas, to do our estimations of the probability. That's how we modeled the probability that y is going to happen when given some x. In this case, you can try to take a few minutes yourself and put this into your calculator and try to run it in your calculator or maybe a computer and get a result. I'm going to give you the answer in just a few minutes. All right, so did you actually get the answer? So let's take a look. We have the answer here reported 0.00576, which now the interpretation is a lot more easier for you to understand. Because this number basically say that we have 0.576% of a chance that y is equals to 1. That means when a person has $1,000 of cash in their account balance, there is only less than 1% of a chance this person will actually file a default in this data set. So that's basically how we are going to interpret the coefficients that we estimate in this logistic model. Again, very different to our linear regression model, because the linear regression model allows you to take this linear format of the equation and try to get the result very, very quick, even by hand. But when you're dealing with logistic model, unfortunately, you have to start thinking about using the logistic function to get the estimate's probability. Now, of course, you don't actually do all this work by hand. You can actually use R, and later we're going to learn how to run the predictions, and the statistical package is going to give you the predictions, the results, pretty quickly. You don't have to do it by hand. But in terms of the concept, I really want you guys to at least know how to get the numbers and how to do the calculations and using the logistic function to get your estimates of the y. Well, we have covered this problem right here, and this time we call this a single variable regression, logistic regression model. However, just like the linear regression model that we studied before, it's not limited to just one predictor. We can actually have multiple predictors to pass into this logistic model in order to improve our fits of the models. So in this case, again, we're using the book example here, the textbook example. So we can actually say, well, from the default or the credit data sets, we are trying to model the default rates. And this default rates, it's being passed in 3 predictors here. In this case, we have the balance of the persons, the income of the persons, and whether it's a student or not. So in order to actually understand the use of this logistic model, you want to actually ask the following questions. If we have all this beta, how are we going to write out our logistic functions? To be honest, it's pretty simple. And in this case, I would like you guys to try to resolve this problem on your own. So Now we are going to basically trying to put this together and write out the estimated probability when y is equal to 1 conditions from the balance of the person has $1,000, the income of the person is $40,000 a year, and the student's identity is equal to 1. That means this person is a student. So to get the probability in this case, you have to use this logistic functions. E to the negative 10.8690 plus 0.005557 in this case times 1,000 plus 0.003 times 40 and plus, and in this case is a negative term, minus 0.6468, and of course times 1. And divided by 1 plus e to the negative 10 times 0.8690 plus dot 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 minus 0.6468 times 1. So that's how you are going to get your probability when the students, it's actually going to be the predictors in your models. So you want to find out, well, how likely this person is going to file a default if he is a student with $1,000 of balance in the account and $40,000 of incomes. Again, I would like to challenge you. So try to compare the two classes here. So the people who report themselves as a students and not a student with the same amount of income, same amount of balance. Do the math, and I will try to talk about the results in just a bit, and you can actually watch the next video to get some intuitions of the models.